All right, welcome to the March Ulta 2025 webinar series. This week, we're going to be talking about ICP-OES, which is the workhorse of many of our labs. And we're lucky enough to have Greg Gilleland from Agilent Technologies today to talk to us about advancing soil analysis with ICP techniques and applications. So, Greg, I will hand it over to you to introduce yourself and to share what you want with our organization today.
Thank you very much, Corey. I appreciate that. I will share my screen. We can jump into things. Thank all of you for attending. My name again is Greg Gilleland. I'm with Agilent Technologies. I've been an application scientist with Agilent for a little over 12 years. I've been in and around ICP-OES for nearly 40 years. So I've definitely seen a lot of things. So I'm going to talk to you a little bit about soil analysis. I'm going to talk to you a little bit about why ICP works, what it does. Let's go ahead and jump in. All right, so the instruments that we're going to be talking about are the 5800 and 5900 ICP-OES. That's just kind of the whole Agilent atomic spectroscopy lineup, all the way from a pretty simple AA unit, a 2-lamp AA unit, all the way up to a triple quad ICP-MS. So we kind of have the whole gamut, but today just ICP-OES. So in terms of what we're going to cover, I'd like to talk about the development and theory of the ICP-OES as an analytical technique. I'll show you some productivity tools on the instrument or in the software that address some of the challenges of ag and soil labs. And then I'll show you some example data. I can't show you everything, but all the data, I tried to fit some gigantic tables on slides, and it didn't work. And I don't want to give you an eye chart to look at. So let's go ahead and jump into development and theory. So as with most conversations in the physical sciences, we're going to start with Isaac Newton. And that's pretty much where you can consider the, I guess, optics to have started, or at least spectroscopy to have gotten a start. He published a treatise in 1666 on light, where he did some experiments using light and a prism, and strangely created something that looked a lot like a Pink Floyd album cover. So after he had done his work, kind of building on some of those things, William Wollaston discovered dark lines on the solar spectra. So he postulated that this had something to do with the composition of the sun, but he didn't have advanced optics to the point where he could really be certain. So fast forward 19 years, I guess, Fraunhofer developed a diffraction grating where he was able to get much better resolution on these lines. And his work kind of started the science of stellar spectroscopy, because he was not only looking at the sun, he was looking at distant stars and making calls on what their composition was. So the Fraunhofer proposed that the dark lines are due to the sun's atmosphere and absorbing the light. So fast forward a little ways further to Kirchhoff and his laws of radiation. Based on some of this work and some of his own, hot dense gases produce a continuous spectrum. Hot rarefied gases, or I guess hot gases where there's not the major component, produce an emission line spectrum. And then cool gases in front of a continuous source will absorb light at specific wavelengths. So Kirchhoff actually worked with Bunsen, he of the famous Bunsen burner, and did a couple of really famous experiments where they placed salt, different metal salts, on a wire loop and placed it into a Bunsen burner, and then focused that light through a prism and looked at the emission lines. So, and this is a crude spectrometer, but it really was the beginning of emission spectroscopy. They recognized the value that it could have in the future. And they actually discovered rubidium and cesium in the process of doing this as well. The absorption experiment was basically just like we mentioned, a continuous light source shined through that flame, and then was focused in through a prism, and then you could see the dark lines where the material had absorbed some of the continuous light source. So basically, I think the take home from all this is that atomic absorption and atomic emission are just two sides of the same coin. You're really, now they don't always line up perfectly one to one, but it's the same process in reverse. So either the atom is absorbing light and you're getting less light through, or the atom is emitting light and you're able to measure that emission. So in terms of the ICP being developed, the plasma being developed, and really it was the plasma that was developed because they hadn't thought of it as an analytical tool quite yet. But Tesla worked on it in the 1890s. J.J. Thomson Lundegaard did some work on flame emission and inductively coupled discharge. Babot experimented with radio frequency ICP in 1941 during the siege of Stalingrad. So that, I think, is the definition of working under pressure. So I thought that was pretty impressive. The first commercial ICP-OES came out in 1974. So it is not an old technique. It's not a very old technique, but it is something that has really matured in the last 15 years and become something that that is kind of an indispensable tool in elemental analysis. Just to talk about kind of how this works, if you think about the Bohr model of the atom, where you have the nice, well-behaved nucleus, and then the well-behaved electrons that are in concentric shells, which of course we know is not true, but nevertheless, if you think about that, it's kind of helpful when we start thinking about what the mechanics are of all this. So in the pretend concentric electron shells or orbitals, you only have the energy is quantized. There are only certain energy levels where the electrons exist. So the energy is determined by the level that the electron exists, where the electron exists. So you take a ground state atom. I've made the atom look a little bit more interesting than just the typical Bohr model. But if you take a ground state atom, same number of electrons as protons, everything's in equilibrium. Well, if you put that into a plasma, and basically what we'll show you is the zones of the plasma and where things take place. We're talking about vaporization and desolvation right now. So in the vaporization and desolvation zone, you have exactly that. You have complete drying of the sample. You have the sample is nearly at the point where it's going to the electrons are going to kick off, or some of the electrons will kick off, and then almost to the point where they'll return and we'll get emission spectra. So I've actually superimposed on this really cool art piece of a torch, an actual picture of a torch running yttrium, so you can see the zones of the plasma a little bit better. Where the vaporization zone is, what you can see, that is the very beginning. That's the bullet, as it were, the very beginning of the plasma as it comes out of the injector. So as you go along up the plasma and watch this process take place, the atom will kick off an electron. In some cases, it's ionized. So this is the ionization excitation zone. In some cases, the electron actually kicks off into a higher orbital, like that. So when this electron either escapes the atom and the atom is ionized, or if the electron kicks into a higher orbital, when they return to their rightful places, then you have light energy emitted. So this is something that Planck worked on and came up with this equation that the change in energy is inversely proportional to the wavelength. So that means when you're looking at very, very short wavelengths like phosphorus at 180, 181, 182 nanometers, you're looking at aluminum at 167. Those are very large energy changes. That's what they represent. And conversely, energy changes like the 766 line for potassium, that's a very small energy change. That is a very, very small jump in terms of energy. So, but this is where we get the emission wavelengths. This is where obviously they're observed as well, but this is where the relationship between energy and emission wavelength is attained. So, just as an example, this is sodium and some of the sodium transitions, energy transitions, and the corresponding wavelengths where they emit. So you can see the 588, 589 wavelengths down there at the bottom. You can see the 330 and the two 330s there at the top. The 330s, everyone will probably know, are not particularly good. The 588 and the 589 are the best lines for sodium, and that just illustrates the fact that the large energy changes are those 330 lines. The small energy changes are the 588, 589 lines. So that's the relationship there. And then you have other emission lines as well. We have a ton of lines that are available. I think altogether in the library, maybe 50,000-ish lines. But this is where they come from. All those lines represent an energy change that takes place in the atom. You don't have to think about it like that. It can be much simpler, but if you want to know the nuts and bolts of why things are working the way they are working, that's it. So I wanted to jump into some productivity tools, some features on the 5800, 5900 ICP-OES that I think address some of the challenges in ag and soils. So let's hop into that. The 5800, 5900 has tremendous matrix tolerance. It can actually run up to 25, actually 30% solids. It is an incredible machine. It's very robust. So there's not a lot that you can throw at it that gives it a problem. It has a vertical torch, so that's one of the reasons it has such tremendous matrix tolerance. It's also got a ridiculously rugged RF generator, so it is ready for anything from the nastiest of all geologic samples or alloy samples to drinking waters to sludges. It is quite a tremendous instrument. So matrix tolerance, great. Interference removal, which I think is probably the actual headline. We have patented background correction, a couple of patented background correction methods. So fitted background correction is something that we have. It's completely passive. It works the same for you as the guy next to you, as your brother-in-law, whatever. It always works the same. There is nothing subjective about it. And then I went ahead there. And then FACT, which is a spectral deconvolution software or spectral deconvolution routine that allows you to take complicated spectra, and I'll show you an example, where there may be a spectral interference nearby, and simplify that, remove that spectral interference, and get back to just reading the analyte and getting the right answer. In addition to that, you have the detector that gives you this awesome wavelength coverage. It does have, like I said, access to thousands of wavelengths, and it's got some features that we'll go into here shortly that allow it to continue to integrate, continue to read, even in the face of extremely rapid read rates. When the charge is really building up, it can actually read those in an adaptive way, which I'll talk about here shortly. And then speed of analysis, just raw speed. The AVS, that's what's shown here. This is a 7-port valve on the left in this picture, and then there's the high-speed valve on the right. This is part of our AVS, which is the automated valve system. This will cut your analysis time from sample to sample in half. So removes the uptake time, removes the rinse out time, which generally is about half or more of your analytical time. So it can tremendously increase productivity. Putting one of these on your instrument frequently will put you to the point where you may not need a second instrument. I mean, I'd love for you to buy one. Don't get me wrong, but you may not need a second instrument because your productivity will go up to that point. It's a wonderful piece of machinery. So let's jump into each of these points. I want to just talk a little bit more about them. So let's go last to first. The AVS, the valve system, like I said, it eliminates the uptake, eliminates the stabilization and the rinse. It does have a bubble injection, a little argon bubble that will go in, and to clean. It actually helps clean out the sample previous to it and gives you nice sharp beginnings of your analytical run. So rather than kind of gradually building up in the plasma, you really get it, and it just jumps up and it's there, and it's stable. So it's a terrific feature. Like I said, 2 times throughput. The installation is tremendously easy. It goes in a little panel that is otherwise empty on your instrument. It comes standard on the 5900. On the 5800, it is an available upgrade. I think it's actually user installable. It's incredibly simple, and I've actually done it, so it should be user installable if it isn't. And it's whole thing fully integrated into the system. The software is part of ICP Expert, so it is seamless, and we work on it. So it isn't a third-party situation where there's finger pointing when things don't go well. So I really like it. Productivity just through the roof on it. So that is where that lives. How does it work? It is a loop. Basically, the valve is used to fill a loop. The valve fills this loop, the little coil thing that you see there, with sample, and then the valve changes state, and the sample is deposited slowly into the nebulizer. And during that time, the probe is being rinsed out. So it's going all the time. So when the probe is in the next sample and it's picking up sample, the nebulizer is being rinsed out. So it's constantly rinsing and doing at least two things at one time. So I think it's fantastic, and it gets you some pretty amazing sample to sample speeds, which I'll show you some later. So looking at the chip, the detector. So most of I guess maybe all of ICPs at this point use a solid state detector, and they use this because most of them use it because the optical system that they're using is in a shell optical system, which means it bends the light, and you end up with an Achelogram looking very much like that. This shape is part of the Echelle optical system. It is the whole system is built around this. And if you can see in the detector, you'll see rows, those silvery looking rows that are kind of at an angle. Those are rows of pixels, and they are actually built specifically for the spectrometer. This was a purpose-built detector. They're built so that light is incident on every single one of those. There is not a wasted pixel on there. It is every bit of it is used, and it all collects light. So it all collects photons and then spits an electron out the back for every photon. So that just like your digital camera works, or the digital camera in your phone, it works very much the same way. So that's what it looks like. That's what the Achelogram looks like. Like I said, that small little area is just pixels, and I actually found a kind of a mock-up so that you can see what's going on. Wavelengths, the shorter wavelengths are at the bottom there, in that narrower part of the Achelogram. The longer wavelengths are up here. So this is basically how it works. And what this does is it splits out the wavelengths and splits out the orders, so that essentially here you have a situation where each one of those lines you could line up with itself. There'd be some overlap, and then the whole thing would be a tremendous spectrum that would be like 30 feet wide. So this is amazing spectral resolution on this thing. It's a terrific optical system. So that is why you see that shape. That is why our detector is built that way. And again, it does have full scan capability with IntelliQuant. And I'm afraid I didn't have time to talk about IntelliQuant today. But if there are questions about it, I can sort of fill people in. But IntelliQuant is a semi-quantitative look at the entire periodic table without the need to calibrate. So it's a really powerful tool, and it will actually guide you as to what wavelengths you should be using for your samples. So if you can scan your samples, it'll tell you about them. It'll tell you what to watch out for. Don't use this wavelength because you've got an interference. Use this one. It's rated 5 stars. It's a great tool. So let's keep moving. I mentioned background correction. So in this case, we're looking at a phosphorus emission line at the 214.914 nanometer wavelength. There is another peak there. We won't talk about what it is yet, but there is another peak in that position. What we want to do with background correction is to get rid of the tail of that peak. The tail of that peak, especially if there was more of whatever that is in there, the tail of that peak would certainly cross over the axis of the phosphorus line, where that red line is, and cause problems. It would give you a false positive signal for phosphorus, especially if none were there otherwise. So something needs to be done. So the simplest form of background correction, which we also have, it's still something that people use sometimes, is off-peak background correction. I'm sure most of you, if you've run ICP, have seen this. You basically set the points, and everybody sets them differently, and everybody thinks they should be in a different spot. So there's always some guy who comes in and says, I think it should be here, and it should be here. And anyway, it's always a discussion in the laboratory as to where these points should be. Very subjective, and the results can vary sometimes significantly with where you put the points. So when we built the first ICP, when Varian built their first ICP, and then Agilent acquired Varian, the onus was on finding a background routine that was not subjective, that didn't involve looking for finding where the best point was today versus tomorrow versus 3 weeks from now. So what ours looks like is like this. So the fitted background correction, or FBC, collects background points all across the spectra, and then develops its own background. It works very well for spectral interferences that are outside of 10 picometers. It works really, really well. Inside of 10 picometers, it starts to kind of have a little trouble. So it's not perfect, but probably 99% of the time, it works sufficiently. It'll take care of your background and give you the right answers, which you can't always say with off-peak. So when FACT doesn't work, or when FITted doesn't work right, we have to fall back on something else, and that is FACT. That stands for Fast Automated Curve Fitting Technique, and it is a spectral deconvolution routine. And what this does, it only requires at minimum a couple of inputs. It wants to know what the blank looks like, just the blank with nothing else. Wants to know what the analyte looks like, and then if there is an interferent, it wants to know what that looks like by itself. So in this case, I'll just drop the facade. That interfering peak is copper. So that's a copper peak sitting right next to that 214 phosphorus peak. So we were able to run obviously we ran the blank to calibrate. We used that for the blank on FACT. We ran a single element copper. We used that for the interferent, and we ran a single element phosphorus, and we used that for the analyte. And using those three pieces of information, FACT drew that red dashed line and got rid of the copper. It doesn't matter if it's the same concentration. You don't have to match the concentrations. It's helpful if you are in the same ballpark, but you don't have to match the concentrations. And it draws that red dotted line, which is the baseline. Essentially, it's creating a baseline so that that entire interfering peak is gone and is out of the picture and not causing you to get spurious results anymore. So I think it's wonderful. This is obviously an example that doesn't show how close you could actually get. If a peak is 4 picometers or over away from your analyte peak, you can correct it with FACT. So it effectively makes your resolution 4 picometers, which is tremendous. So I think this is a great tool. It's wonderful. Now, I'd like to jump into some data from some samples. I have over the last few months run some ag samples, some soil extractions, and we've got some soil data in general that has been digested, or soils that were digested. So we'll take a look at some of this, talk over, or I'll at least discuss the results. And then after that, I think I'll turn it back over to Corey and we can open things up. So the first thing I wanted to do was show you some malic soil extraction data. This happens to be for phosphorus. I had a bunch of elements. I just picked one, and phosphorus seemed like a likely candidate. So I ran 4 different phosphorus wavelengths, and you can see even at a relatively modest level, about 100 ppb, I had tremendous precision. And obviously the next couple are even more concentrated, and the precision is spot on. The variation between the 4 wavelengths, I've actually got that last column shouldn't say a phosphorus 177. It should be the averages. My apologies. But the averages and the percent relative standard deviations are pretty amazing on 4 different emission lines for 3 replicates of the samples. So I was pretty impressed with the ability to replicate data here. I've got another set of data. This I think is boron from another malic extraction, or I guess there were three malic extractions, and you can see again the precision even at a very low level. If you look at that second data set, the average is 3 part per billion. And I got a 16% RSD. To me, that's pretty tremendous with 4 wavelengths reporting. So I was very impressed with that. It is a very solid, stable instrument, and it handled this in stride without any problem. So I could run. You could run these all day. Spike recovery. I actually did spike a couple of samples, a couple of the malics. You can see the spike recovery results there. Some of them, let's see, I'm looking at that first line. The sulfur is a little bit, is kind of low, but the spike was only 2 ppm and the sulfur was 15 ppm to begin with. So that was going to cause a problem. I think the second line looks pretty decent. Potassium, 85%, not my favorite. Aluminum had a negative 37%. We didn't just vaporize aluminum. The 54 ppm, 50-ish ppm of aluminum just ate up my 2 ppm spike. So it was a non-starter. But everything else that was in range looked great. So the malics, I thought, ran very, very well on the system. So I also acquired detection limits. So I spiked a standard at 10 ppb and ran it 10 times and took 3 times that standard deviation. So you can see some of them I have multiple wavelengths for, some of them I don't, but pretty darn good detection limits, especially considering the fact that I really wasn't trying to optimize detection limits. I really just wanted to run the samples and get good reproducibility, but the detection limits came out of it looking very good. Also wanted to show you some plant tissue sample results. This is more boron. Again, you see the reproducibility between the 4 wavelengths, and the even over 4 separate samples and 3 runs each. The reproducibility is tremendous. I can't say enough about the instrument. I love it. I think it's amazing. I've been running ICP for an awfully long time, and this is just the best. So at the end, I wanted to show you something about speed, because what the instrument, I've been in soils labs, and they are cranking out samples like crazy, as I'm sure all of you know. And their busy season is like a busy season like no other lab that I've ever seen has. So speed is of the essence. And I want you to look at the time signatures on these individual runs. This is about 14 seconds a sample. There's actually, I actually have a one that's a little faster. It's about 8 seconds a sample, but these are unbelievably amazing numbers. This is, granted, there were, I guess, compromises. It was a one replicate. I think there was maybe a couple of seconds of rinse time in between, but this is just banging out samples at an incredible pace. This is with the AVS, the switching valve, but 14 seconds, is it 14 seconds? Yeah, 14 seconds a sample. I just thought was amazing. It kind of blew me away. So I wanted to be able to share that with you before the end of the presentation. So I appreciate your attention, and I would absolutely answer any of your questions that you had. And I'll throw it back to Corey.
Right, Greg, thanks so much for that presentation. I know we hit a lot of topics there, and I know I have some questions. I would encourage folks who have questions to put those in the chat at this time, and we'll walk through. We may just kick it off with my questions first. I do want to remind folks that are certified crop advisors, you can get a CEU for this presentation by using the QR code. If the QR code doesn't work, which I know sometimes there are issues, you can also email me and I'll make sure you get taken care of. Greg, one question that kind of came to mind when you were talking was, sorry, I'm trying to think how I want to ask this. I guess so we heard about kind of the history of ICP-OES from you, but what's the next thing? What is like the thing that's going to revolutionize the ICP industry? In the future. You've been in it for a while. What are your thoughts there?
Well, I think, first of all, I think the whole thing's headed to a tricorder. We're all going to carry around tricorders, and at that point, I will be out of a job. So I'm hoping that we can just stay with the current models or something similar for 5 years, so I can retire. But that said, I do think that we're seeing tremendous advances in basically making things smaller and easier to use, and I think incorporating AI into these software programs and working that way. I think AI is really going to revolutionize this, because it will be like having a crusty old spectroscopist helping you all the time, without having one actually there or paying one, which is really good. So that would be my take. I think AI is really going to make a huge splash in spectroscopy.
So that's actually interesting. Yeah, I wonder about the data review component of using artificial intelligence in that way too. We do have a couple questions that came in the chat, and this kind of goes to that quality control, quality standards, quality assurance. One question was, can you run with an internal standard? So before you start, can you explain what an internal standard is? Maybe make a recommendation, because I know different labs use different internal standards.
Very
and then
true.
Expand.
Yes, the quick answer is yes. You can run with an internal standard. It's super easy, and I would have gone into it, but again, I was concerned that I was going to talk too much. So I tried to cut some stuff out. But internal standard is basically what an internal standard is you add a known amount of an analyte that is not in your samples, that is also an analyte that is not something you're looking for. You add that to your samples, and in fact, I always add it in line. So I have a tube to a vessel with internal standard in it, typically yttrium, germanium, tellurium. Those are the three that I like because they cover a range of ionization energies. And then your other line comes from your autosampler. So they go into the nebulizer, and then your internal standard is basically a ratio, and it ratios everything to the first run of the internal standard that runs with the blank. And after that, if the internal standard is suppressed, then it assumes that all the analytes that are tied to that internal standard are suppressed. So it normalizes the internal standard back up to 1 and normalizes the samples up the same proportion. So all those analytes that say were tied to an internal standard that had a 97% recovery will be normalized up 3% to get that internal standard up to 1. So that's the purpose of an internal standard. It basically helps you account for things like viscosity changes, matrix changes, any sort of matrix suppression. That's what an internal standard does.
Yeah, so I a couple things I'm going to expand on that, and then I'm going to jump ahead one question because it's following up on the internal standard conversation. I know scandium is also a common internal standard used in our labs. One challenge that I think a lot of labs have, and I think maybe this is what the person asking the question is getting to, that I'm about to ask, is sometimes the internal standard seems to actually be throwing off results, and I think it's related to speed or maybe how we have it set up. Because I know there are some labs that are adding an internal standard actually to the sample. As you mentioned, an inline injection, so the sample's being brought into the ICP, and as it's being brought in, the internal standard's getting mixed at the same time, as opposed to adding the internal standard somewhere in almost the extraction or post-extraction process to the sample.
Right.
So the question that was asked is, do you recommend using an internal standard with very rapid soil analysis? And so can you expand on that a little bit?
I would prefer running internal standard all the time. If there's something, I don't know that there would be a speed advantage to running without internal standard. It doesn't take any extra time, but I would say that I don't think it takes extra time to run internal standard. I think if you can do it, if it's available to you, I would absolutely run internal standard. There isn't really a downside. I guess if there is a downside, you're diluting your sample by just a very little bit. Typical configuration would be like a white tubing, a white peristaltic pump tubing, which is 1.04 millimeter ID, and a orange green tubing, which is 0.38 millimeter ID, which works out to about a 9-to-1 dilution. So your sample is diluted by 11%. So it's not much. And I don't think there's a good reason not to. I think if there is a problem with internal standard, I think it could be because in high matrix samples, you don't have enough. You have so much ionization going on with the group 1 and 2 elements that you are seeing EIE effects. I would suggest maybe using a cesium ionization buffer and seeing what that does to your results.
So I followed up in the chat there just asking if the question was regards to slowing down analysis time or actual issues with the actual analysis. And so we may dive back to that question here in a second. Oh, well, there you go. I've observed that the initial reading is not representative of the internal standard reading later in the run. TEG, the initial is 100%, but everything later is lower. So I will say that I've worked with a few labs that have this issue, especially when they're using scandium. I don't know if it's scandium specific, but that's the lab, the internal standard being used. They're in line. they're using an internal standard. The internal standard initial will come back at 100. If you run blanks, it will come back at 100, which that makes sense. But when you're running actual samples, the readbacks will be either, I'm not sure about in Jim's case, but in my experience, it's usually several percentage points higher. And when you look at how it's correcting the data, it actually causes some issues. And so that's where I know some labs have switched to they have an internal standard, but they're not doing a correction with it. They're just using it as a QA QC if something happens, or to trigger the instrument, right? If the internal standard drops to 10 or goes up to 200, there's a plug or something's wrong and it stops the instrument. Do you have any thoughts on what would be causing those kind of issues?
I come back to ionization, I think, and also what elements are they seeing that are affected negatively? Obviously, if you get a 150% internal standard recovery, then everything attached to that gets negatively affected. But I will say that elements with higher ionization energies in high matrix samples, they do better with a high ionization internal standard, like tellurium or germanium. So they will behave, those elements will behave more like those high ionization energy elements like phosphorus, boron, things like that. They'll behave more like those than yttrium or scandium, if that makes sense.
Yeah, I think that what you're getting at is that choosing that internal standard is really key, and that maybe that changes by instrument even. And so there may be some need for labs to play around with that.
It's definitely not one size fits all. It's definitely not one size fits all.
So another great question, and this is I think this is a conversation a lot of us have who work with ICPs because we deal with plugs in the nebulizer. And so the question was, what nebulizer did you use in the Malick 3 analysis? And maybe make some recommendations on nebulizer choice after you answered.
I used the One Neb, which One Neb Series 2, I guess, which is it's a nebulizer that we have that's made of a polymer. So the nice thing is you can't break it. It's super robust. The capillary that runs through it is the same size all the way through to the end of the nebulizer. So if it's going to clog, it'll clog way back before it ever gets to the nebulizer. So it's super robust. It's also very efficient. When we go looking at, if we're gunning for detection limits to try to get the lowest possible detection limits, we'll pick the One Neb and maybe even a single pass spray chamber so we can get max signal if we're really pushing detection limits. It's a great nebulizer, and it's also very, very good with high matrix samples. The second half of the question was a nebulizer recommendation, or?
Yeah, I mean, just consider it. So I know that several labs hear from their partner, their ICP partner, hey, you're having problems with plugging, you're not, maybe try this nebulizer versus that nebulizer. And so just what are some, without highlighting a specific product or anything like that, just what are some considerations labs should be thinking about when they're looking at nebulizers, or maybe testing new nebulizers?
If you are having nebulizer problems in terms of your nebulizer salting up or getting deposits right at the very end of the nebulizer, I'd look at an argon humidifier, some sort of system to humidify the argon going through, because it has a tendency to dry out right there at the end of the nebulizer. And if you're carrying a big dissolved solids load, it can drop right there. And that can give you a lot of sputtering and weirdness, and could potentially block your nebulizer. If you're seeing clogs, repeated clogs, first of all, I guess my question would be, are you filtering samples? And I know that they don't always filter samples to, when I run samples, I can run 10 samples and that's my day. And I know they're running 2,000 samples and that's their day. So I understand the difference in scale. There are things you can do, at least on our auto sampler, which I'm sure you can do with other auto samplers, to control the depth of the probe into the tube. You can also use a different nebulizer, such as the V-Groove. We have a V-Groove nebulizer And actually, we just reintroduced the V Groove a couple of months ago. I'm sorry I mentioned the product. I didn't mean to, but anyway, there is a V Groove nebulizer that is super robust, and they actually dare you to block it. So it is. It is. I think that would probably be my. It wouldn't be my first choice necessarily, but I would certainly consider that as a possibility. Some sort of V Groove neb.
Quickly, what would make a nebulizer? So when I think about nebulizers, I think about either you have sensitivity or you have robustness.
Mm-hmm.
What is making them more sensitive or improving your sensitivity versus making them more robust? Is it just the hole size, the diameter of the internal capillary, or?
Well, it's the internal capillary and the flow characteristics through the capillary. I think when I was 20 plus years ago, when the Earth was still cooling and I was doing this the capillaries inside of the nebulizers were long and tiny, incredibly thin. They've kind of evolved to the point where they're not tiny until they get to the very end. You don't see those needle-sized capillaries all the way through the nebulizer for most nebulizers anymore. So I think those studies of the flow through that capillary and studies that optimize the aerosol creation, and also if you're running an ag lab and you're using a single pass spray chamber, you need a double pass. The number of particles, you're putting large particles into the plasma when you're using a single pass. You want to use something that minimizes the particle variability. So a double pass will only take certain particle sizes. It really, a spray chamber is a particle size separator. So that's something to think of as well. And I'm kind of jumping around, but I get all excited about these problems and I want to like shotgun them and just like jump in and start fiddling around with things. So
No, I love the energy, Greg, and I think you're highlighting that maybe there's a whole nother webinar just on ICP sample introduction systems. And these kind of considerations. One other question that came up in the chat, I have the person spoke and said, I have a question about running mineral digest of soil samples on ICP-OES. What is a good practice to sample soil for mineral digest? Should we focus only on finely ground soil, complete powder, or take a representative sample with some small grains?
Well, I guess that would depend on what your purpose is. If you're trying to see what will leach out naturally, then I would leave it as close to natural as possible. If you're looking for as close to a whole rock digest as possible, or as close to a whole total digest, in some cases people actually want to dissolve the silica. So if you're going to throw HF in there, yeah, I would take it down to a very, very, very fine powder and use that, because you're optimizing surface area because you're trying to get as much into solution as possible. So it comes down to what your purpose is. Like if you're a mining company, yes, mill that thing down to a very fine powder and then run it. But if you're doing environmental studies, some kind of leaching study, I would definitely consider leaving it at a larger grain size.
So I think most of our labs, we're working on a soil fertility situation where we're doing a Malic 3 extraction, and then it has to be compared to some kind of land grant university or some other interpretation of that. And so I would just say, everyone should make sure you're grinding that matches kind of those standards there. Bob Miller, are you available? Can you come on? I know you've done some grinding studies. I'm just wondering if you have some thoughts on this, Bob.
Yeah. Thanks, Corey. So the bottom line is most of the flail mill grinders that soil testing labs use, you're just beating this stuff down to a pulverizing size, and everybody thinks that they're getting 2 millimeter minus, and they probably are. But the problem we have is that you get this wide variation in particle distributions. Yeah, 50% of the particles are below 1 millimeter, but still got a several large portions of it that are above that. And again, it's a function of texture. If you're in a sand, well, you're limited to basically the grain size of the sand and the fact there's not much aggregation. But the bottom line is, we did a study, gosh, this is 15 years ago. where we used 4 different kinds of mills to grind the samples. And then we looked at the particle distribution on screens, what we got. And then we looked at the lab analysis. And the bottom line is that the finer you grind it, and I'll say below 1 millimeter, the more homogeneity you get. So this is a big hot issue in the carbon market right now because to get really good measurement uncertainty values, very low, you got to pulverize soil samples down to 0.2 millimeters. So,
Bob, thanks for jumping on there. And I should have introduced you better. So Bob Miller is Alta's academic or science advisor. I don't know, our regional, or not regional, national expert on soil testing from an academic realm. And so thanks, Bob, for for stepping up without any kind of warning to that question. So
no problem, Corey. Later.
yeah. So Greg, real fast, I stopped sharing. I'd love for you to reshare your screen. And I got texted a couple questions about some of the detection limit stuff you did on the back end of the study.
All righty. Okay.
So if you want to go back to those detection limits.
Yep.
I think in the soil analysis, yeah, go back a little bit more.
There.
Yeah, so Malik 3 detection limits. I got the question, and I think this is really valid. So this was in Malik 3, but with like a chemical elements added, correct?
Yes.
Did you do anything with, or have you played around with detection limits in an actual soil extraction? So just low levels of soil? Because what we see in soil, so many other chemicals that there's a lot of interference. And
there is a lot. I didn't have an opportunity to really take a lot of time with this sample set, but so no, I did not do that. But I think that's work that should be done. I think it would be very interesting to see.
So my question is, if you were going to establish those method detection limits on actual soil samples, obviously soil is an environmental substance, right? We can't really control what's in the soil when we get it. Is grabbing a soil sample with a known value and then adding, like, say I want to determine phosphorus, grab a soil sample with a known value and then extract it how I normally would, maybe several times, and then add like a very small amount of phosphorus and to figure out how much of that increase. Is that a good way to determine where my detection limit is on that, or what are your thoughts there?
I think so. I think that reading an incremental increase at a very low level, and it's like a spike, but only it's a much lower spike. I think that's you're onto something there. I think we could do that and probably get a really good read on what you can see in the extraction itself.
Well, and I think a lot of our labs, we struggle with phosphorus using usually an issue. There's so much phosphorus in soil, we're nowhere near the detection limits a lot of times. But for some of our micronutrients, you had aluminum. I think manganese is a great example.
Mm-hmm.
Those sometimes can get pretty low. And so understanding where that detection limit is, I think is really, it's just a key question that sometimes we don't jump onto. My other question was, if you go forward to the plant tissue, do you know, and I know this is really random, but do you know what extraction you did on the plant tissue samples?
I do not.
Okay.
I do not.
It was
know
some
what
kind of
extraction
acid
was done.
digestion, probably.
I don't know what. I don't know. I mean, it may be buried in my notes somewhere, but I do not know what kind of extraction was done.
No, that's fine. That's fine. Just was curious there. So as we kind of wrap up, I would just love for you to share. I know that you've worked with several, I think several labs on this call, but definitely several of our Alta members. I would love for you to share what are some of the challenges that that folks have run into in the soil lab when working with ICP or ICP-OES. What are some, like, is there any just in your mind something that stands out as this was a really odd situation that came up? And it was one of those things where it took a lot of problem solving to figure out what it was or anything like that. Do you have any tips or suggestions, thoughts there?
Now I'm on the spot.
Yep. Sorry.
Well, I think, first of all, I think the soil lab, the biggest problem is just keeping the instrument running and running properly. and the constant upkeep of the instrument, making sure that the sample age reduction system is properly set up, and that your tubing is good, et cetera, et cetera. And I don't think people have enough of an appreciation for peristaltic pump tubing and the amount of, I guess, punishment it takes. I think that is the Achilles heel of the ICP, and if that is not right, bad things are going to happen. It needs to be. You need to learn how to tension it properly. Tensioning a peristaltic pump is a delicate thing that needs to be done properly, and then it really shouldn't have to be done again for that size tubing. If you just run, white in that pump position, you should never have to tension it again. There are a lot of people who come in and want to crank the tension, and it wrecks the tubing, and then makes all subsequent tubing last shorter time. So I'm sorry I don't have a tremendous. I'd have to think about it for a long time, especially with only one cup of coffee. But I think that's to me, that's the biggest problem.
Greg, I'm gonna make that the clip on this. ICP people don't appreciate the complexity of peristaltic pump tubing, or it's the Achilles heel of ICP-OES analysis. I see a whole presentation on that topic. But I do love how I think it highlights one thing, which is that some of the biggest challenges when it comes to ICP-OES is sample introduction systems. And so I appreciate you kind of pointing that out and highlighting that for our members. So not seeing any other questions. I appreciate everyone joining us today for this topic. It will be recorded and available on the Alta website, hopefully by, this weekend or early next week. And I encourage people to share it and review it internally if they saw value in it. And with that, Greg, thank you very much. And we really appreciate your time.
Thank you, Corey. And thank you all for attending.